which leaves me with nothing much more to say from the organizational side. So let's start diving into the topic. Today it's going to be about shifting left our tests. We're CQSE. We're a company dedicated to the topic of software quality and quality improvement for about 15, already almost 16 years by now. We're seated in Germany with a headquarters in Munich, but we're spreading throughout the world because obviously the topic of software quality is important for so many people around the world that, yeah, this is a growing business here. We're also developing our software intelligence platform TeamScale as a tool, which is also offering the features we're going to talk about today, helping you shift left your tests even if they are running slowly. And I'm very happy that we have Fabian and Johannes here as our speakers from our test intelligence team who will guide us through this topic. There's no more experienced people in this area than the two of them. So I'm very much looking forward. And since you're all here, you already told us this is an interesting topic to you as well. So I'm looking forward to both interesting insights from Fabian and Johannes, as well as lively discussions with all of you. Fabian, take it away.
Thank you, Sven. All right, thanks everybody for joining. My name is Fabian. As testers, we face a dilemma because on the one hand, successful software grows. That means we usually don't remove any features from our software. We just keep adding more stuff to it. So there's ever more code to test. On the other hand, release cycles are getting shorter and shorter. So there's less and less time to do the testing. So we have to be more efficient and more effective with our testing. And shift left seems like an answer here. So running our tests more frequently and earlier in the development lifecycle, so we can give feedback on new bugs that were introduced much earlier and much more frequently. Unfortunately, for most of my customers, the really valuable test suites, these end-to-end test suites that find the really interesting bugs, they take hours, days, or even weeks to run. And with such a large and long-running test suite, it seems kind of impossible to shift left and just take all of these tests and run them more frequently. Because most of these teams have already reached the end of what they can do economically with parallelization, virtualization, and so on. So there's no easy way to speed up these test suites and shift left. Fortunately, in research, there is a very simple idea how we can still shift left even if our test suites are this long running. And it's called test selection. The basic idea is, why don't we take a small subset of our test suite that, for example, only takes a few minutes to run and run that much more frequently? And if we do this in a way where the small subset has a lot of bug finding power, then we can find most bugs much earlier with just a small subset. And this is what I'm going to show you today. We're going to go through 4 different approaches how you can do this test selection. And we're going to need some good tricks to concentrate that much bug finding power in these small tests. So I'm going to show you these tricks and how this works. All of this is possible with our tool TeamScale. So we also have 2 demo sessions where we show you how this works in the tool. But before we dive into all of the details, a little bit about myself. My name is Fabian Streitel. I work for CQSE as a team lead. I lead the team called Test Intelligence. So my team is responsible for all the different smart analyses in TeamScale that we have to make testers' lives easier. And this includes this test selection, but also other things. And as that team lead, I basically wear 2 hats on my head. One is the research hat, where I help supervise bachelor and master theses to find out new ways and new analyses that can help testers. And it's great to find interesting results in research, but often enough, it's unfortunately the case that what looks good on paper in research isn't actually transferable to real industry projects. So my second hat is the construction hat here, which means I'm working in real customer projects to bring these analyses into practice. And all of the approaches that we show today have passed both of these tests. So they are backed by research, but they've been also tried in industry projects, and they work even if you have a large legacy system, legacy technology, or a really, really large test suite. So let's jump into test selection. I'll first start with the general idea and how it works and what some of the constraints are, and then I'll go into the different approaches. Imagine for a second that this is your test suite. So every rectangle here represents one test, and the green sort of shows that they do different things. When we do this test selection, then we want to select a small subset of that test suite. Now, if we were to run all the tests, then some of them would fail, represented by the red X here. And they would reveal some bugs. Usually, it's not the case that one bug causes exactly one test to fail, but rather, as is the case, for example, for the orange bug here, it causes 2 tests to fail, and the blue bug causes 4 to fail, and so on. This is already a simple fact that helps us, because when we make a selection from that test suite to run that selection more frequently, we don't need to have all the test failures in that selection. So for example, for the orange bug, we only have one of the 2 failing test cases in there. But when we see this failure, we can already start debugging this bug, we can fix it, and then the second failure will be fixed automatically as well. So that already helps us. There's a second interesting observation we can make here from this example. Not all of the bugs are represented in this selection. You can see this down here, for example, with the purple bug. So none of the purple bug test failures are in this selection. This may look like a problem at first, but in practice is actually not. Because how do we use this small selection of tests? Imagine that this is your testing process. So you have your main line, and on that main line, you very infrequently run your test, let's say once a day or once a week. And in between, a bunch of additional changes come in. So in your current test process, you find all the bugs that the test suite can find whenever you do this complete test run. Now with this smart selection, we can add additional test runs that are really fast because the selection is small. And if we achieve it, that a lot of bug finding power is concentrated in this small subset of tests, then most of the bugs will be already found much earlier in these smart selection runs. So basically, we're shifting most of the bugs to the left and find them earlier, give feedback about those bugs much earlier, and only a small percentage will remain, and we will still catch them in the same interval that we catch them today, which is whenever you do the complete test run. So with this technique, we're not really losing anything, we're just gaining much faster feedback on most bugs. Now, I already mentioned we'll need some tricks to really concentrate a lot of bug finding power in a small amount of tests. So what we did is a lot of research, many of these bachelor and master theses and papers on this subject, to try out a lot of different approaches how this test selection could be done, and find out the ones that give us the right results and are applicable to industry projects. And I'll walk you through 4 different ones. Now, the first trick that we're going to use is that these end-to-end test suites, these really long-running test suites, they are usually highly redundant. What do I mean by that? When you think about these test suites, the way they evolve, the way they grow, is usually by copy and paste. Meaning that if you want a new test case, you take an existing one, you make some minor modifications, and then you have your new test case. What that means is that you, in the end, get a lot of test cases that do a lot of the same things over and over and over again. And we can use that redundancy to squeeze out a lot of bug finding power into a small amount of tests. And to show you how this works, I'll use an example. This is Pixelitor. This is basically a drawing program somewhere in between MS Paint and Photoshop. And it's open source. And I'm using it as an example, not because a lot of our customers make drawing programs, but because it's something that I think everyone can relate to. Everyone has worked with this before. So when I show you the different test cases, you can understand what's going on. Now, this has an end-to-end test suite that automates the UI. And I want to show you a few facts about that test suite. And for that, I'll need a visualization to show you the source code and the tests. And we'll use this. This is called a tree map. Now, if you already know us, then this will be very familiar to you. We like to use tree maps all over the place. What this is basically a visualization of the whole software system, so all the code in there. And every rectangle here corresponds to one component of the software system. The more lines of code in a component, the bigger the rectangle in size. And I'm going to iteratively step into these components and first draw all the classes in each component, and then draw all the methods in all those classes. And then we can use color to visualize what we know about this code. For example, test coverage. Everything that is green here is covered by the end-to-end test suite. So this code is getting executed when you run the tests. Everything that is gray is not covered by this end-to-end test suite. And we can not just do this for a whole test suite, but we can do this for each test individually. Then you get a picture like this. And I'm claiming these tests are very redundant, and we can see this here. But unfortunately, these rectangles are so small, it's probably hard for you guys to see this on the screen. So what I'm going to do now is I'm going to simulate running this test suite and go through the first few test cases and show you the coverage of each test case. Now, when you run this end-to-end test suite, the first test that is getting run is called test Gaussian blur. So this is testing some blur functionality in the drawing program, and this is the coverage. When we go to the next test case, it's called test motion blur. So you can see this is a sort of related functionality. Again, we're blurring something, but with a different technique. And now we have a second color. So blue here means this is code that this test is covering, this motion blur test, but that was already covered by the Gaussian blur test. So you can already see those tests are covering a lot of the same code. There's much more blue than green here. If we go to the next one, it's even more pronounced. This is test lens blur. You can again see blur, 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 sort of all similar functionality. And of course, these tests have similar coverage. And if we do this not just for these test cases one after another, but for the whole test suite, then we can get a graph like this, where we have the test suite runtime at the bottom, and on the y-axis, how much coverage we've achieved after each of those test cases in total. And 100% over here means not that we have covered the whole software system, but that we've achieved all the coverage that you can achieve with this test suite. And what you'll notice immediately, I guess, is that there are a lot of plateaus here. And this is exactly where we're running very similar test cases one after another that are really redundant with each other. Because each additional test case doesn't really add much additional coverage here. Now, how does this help us to shift our tests left? If you think about making a small selection from this test suite, obviously it makes no sense to, for example, take only tests from this plateau. Because then we're only able to find bugs in a very narrow part of the application where all of these tests are testing sort of the same thing over and over again. It would make much more sense to take very different test cases, for example, all the ones that make these large jumps in coverage here. And we can find bugs all over the system because we picked very different test cases that test very different areas of the application. And this is the first idea, the first approach that we call Pareto optimization. Now, let me show you in this example what happens when we run this Pareto optimization. We get a different order of the tests. The first one is called test create and modify selection. It has this coverage. You don't really need to understand what these tests are doing now. The second one is test change view settings. You can see there is some blue here, but there's more green than before. And the next one is test second layer. Again, some blue, but still more green than before. And you can hear just from the names, it's not blur, 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 all the same, but rather very different parts of the application, and also in the coverage, different areas of this picture are being covered. And if we do this for the whole test suite again, then we go from this picture that we had before to this picture. And you can see that this is a dramatic change. Now with only about 5% of the test runtime, we can achieve almost 100% of the test coverage that the whole test suite can achieve. Just by reordering these tests and taking the ones that produce very dissimilar coverage to the front. So this Pareto optimization basically as input needs this test coverage for each individual test case. And we can do this for both automated cases and manual test cases. There are techniques as well to record this kind of test coverage for manual test cases. And with that, we get this sorted list of tests, and then we can decide how much test budget do we want to spend and cut off from the front as many tests as fit in the budget. Let's say I have 50 minutes to spend on testing, then I just take tests from the front until the 15 minutes are full. And that's my smart test selection set, and I run this very frequently. Now, how well does this work in practice? We try all of these approaches, both on open source systems and industry systems, when we make these research studies about them, to make sure that we have a lot of different systems in there and try it out on different systems to make sure it works for all kinds of software systems, and to have industry systems in there to make sure that we're not relying on some preconditions that are not fulfilled in industry projects or need data that industry projects can't provide. And when we tried this out, on average, we need 11% of the time to find 90% of the bugs. Now, this is really a great result, because if you imagine at the moment you have a nightly test suite that takes almost a whole night to run, then with this approach, you can turn this into something that you can run multiple times during the day and find 90% of the bugs already during the day instead of having to wait for the next day. So we can already use this in real projects to speed up and shift left our tests. Now, it has some disadvantages too. It relies on this test coverage, so we need to record coverage for each individual test case. This is some setup effort, and of course, it also is some maintenance effort, because as the software system changes and as the tests change, we need to update this information continuously. So that brings in some complexity into a project. And for some really complex large legacy systems, this may still be too much effort to actually implement such an analysis. So we also looked at other approaches that don't have this problem, but still can give us good performance and allow us to remove the redundancy from these test suites. And so the second approach that I want to show you does not rely on test coverage. Now, if we go back to the way we did it with test coverage, the idea here basically was to break up these clusters of very similar test cases. Now, test coverage is one way to decide if two test cases are similar, but it's of course not the only way. If I give you, as a human, two test cases and ask you, are those similar, then you can tell me that without having to look at the test coverage. So we can find other metrics that decide if test cases are similar or not, and use those to break up these clusters and remove this redundancy from the test suite. Now, no matter which metric you use, this basically turns into a clustering problem. So this means that if we take all of our test cases represented by these bubbles here, then we can put them in a vector space so they get assigned coordinates. And we have to do this in a way so that similar test cases are clustered close together. And when we achieve this, then we can start with any test case and always pick the next test case in such a way that it's furthest apart from the test cases we've already picked. So this second one is furthest apart from the first one, and the third one is furthest apart from the first two, and the next one is furthest apart from the next three, and so on. And this way we can, again, have very dissimilar test cases without needing to know the test coverage. We tried dozens of metrics here to see which ones are actually feasible to implement, are fast, and produce a really good selection result. And you can start with really simple metrics like how many characters are in a test case, and then go to more complex things like edit distance or which concepts are represented in the test case and so on. The one that worked really well is actually using AI, so large language models. But maybe not in the way that you think, because we're really only using the first part of these large language models. Because what does ChatGPT or Gemini or whatever other model you have do when you give it any text? It turns it into vectors of numbers. these are called embedding vectors. And they basically represent the semantics that the model is extracting from this text. To make it a really simple example, let's just take a single word like man or woman. And if we feed this in, then we get one of those vectors. Now, this is simplified because in a real large language models, these vectors have hundreds of entries, not just 6 or 7 like we have here. And in a real large language model, we also don't really know what each of these numbers represents. Like we have these categories written up here that these things are supposed to represent. But for large language models, these are not given a priori, but rather the model learns these categories on its own during the learning process, and we don't really know what each number represents. But we don't need to know. We only need this property that similar words and similar texts get similar vectors. And this is fortunately given for all of these large language models. So you can see this again very simple in 2D on the right, where man and woman are sort of close together and king and queen are sort of close together. Now with these vectors, we can do this clustering and then select very dissimilar test cases. And then again, we spend a test budget of, let's say, 15 minutes and take the most dissimilar test cases until the 15 minutes are full. And that's our smart selection that we can run very frequently. How well does this work? Now we need only 13% of the time to find 90% of the bugs. So this is a little bit more than before. Pareto optimization had 11% of the time, but we don't need this test coverage anymore. So there's a lot of saved effort. We only need the code for automated tests or the test steps for manual tests. And this means there's much less effort to set this up initially. And once it's set up, it basically runs automatically because we can just continuously query the current state of your tests from either your version control system or from something like Jira or X-Ray or what have you, where you have your tests. And then all of the optimization happens automatically. No need to continuously record this test coverage. It does have some drawbacks, of course. None of these approaches is perfect. So since we're only looking at static information about your tests, we cannot take any runtime information into account. This means if your system, for example, has variants and your tests behave differently depending on which variant you run them on, then this is not something that we can put into this test selection approach. Or if you have data-driven tests and you can run the same test with 50 different inputs, then we can't tell you which of those inputs to use because this is not part of the information in the test case itself. If this is the case, then you might need Pareto optimization. Otherwise, AI test clustering is probably good enough. So you can already see how these different approaches are all valid. They just fall on a different point in the cost-benefit spectrum. And depending on how much pain you have and depending on what your test setup looks like in your software system, one may be more applicable to you than the other. So far for theory, does this actually work in practice? I have one use case from one of my customers.
Fabian, let me jump in here.
Yeah, sure.
Because we have a question, perfectly valid question in the chat, which I like to bring to everyone's attention. The code is of course not fixated, and tests need to test changes because any changes you introduce might also introduce bugs, and they might also introduce like additional steps in the graph when you look at the coverage. So maybe you can say a few words how this approach relates to us changing the code base.
Yeah, excellent question. So I think there's two parts to the answer. One is basically what I said on this slide. When the code changes, of course, the coverage of the test cases may change. So in regular intervals for this Pareto optimization, we need to update that test coverage information. So we still have the correct information about the test cases. Usually our experience is that you don't need to update this every day, but rather this is rather stable information. We've done some tests on industry systems to see how quickly does this coverage information degrade. And for this Pareto optimization, it's enough to update this once every few weeks, and for some systems, even only once every few months. The AI test clustering approach does not need that. Here we just need to update information about the tests themselves because we're not using the test coverage. Now, the second part of the answer is you're also right that when things change, most bugs will probably be located in the areas that we changed. And these two approaches that I showed here, they don't really care about what changed. They just output you a list that is fixed, and you run this no matter what changed. And we still can find 90% of the bugs with this because we're testing all over the place in the system. So we have a good chance to catch bugs no matter where you make changes. In the second part of this presentation, I have some tricks that actually target more specifically to what has changed that allow us to get even better performance out of these approaches. So I would ask you to stay tuned for the second part.
Okay, awesome. Thanks for answering the question. I hope that gave that answer to everybody. And if
Thanks.
you have
And
more
thanks for the
questions,
question.
everybody just chime in.
Definitely. All right. I'll give one example of of real usage of the Pareto optimization in one of our customers, which is Bayerische Versorgungskammer. They are an insurance company, so they have your typical business information systems. And one of their systems had a test suite when we first met them that ran for 12 hours. So it was just about possible to run it once a night. So you start it in the evening and then it's done the next day before the developers come in and want to look at the results. But they were expecting that this test suite will increase over the next years because they're adding a bunch of new features. So it would not be possible anymore to have the feedback from this test suite the next day. And it would turn into something like a bi-daily or maybe even weekly test suite. So they were very interested in speeding this up and shifting this left. And they tried out Pareto optimization. And for them, with only 5% of the test runtime, so less than 1 hour, they can already find 70% of the failing code changes. So that means they are now running this very small, less than 1 hour test suite multiple times during the day. And they're not just maintaining this nightly test suite as something that they can get feedback on the next day, but rather they find most of the bugs already during the day. So for them, this really helped them keep fast feedback going and even speed up the feedback cycle, even though that test suite grew a lot. Now, before we go into a demo of what all of this looks like in the tool, are there any more questions that came to your mind about these two approaches where we try to remove redundancy from the test suite and this way speed up your tests?
Currently, there's no questions in the chat, but
Can I ask it by voice? Is it fine?
Yeah, sure.
Am I understood correctly that you are trying to connect basically the code coverage with end-to-end tests, right? But end-to-end tests, usually it's just, it's not related to the code coverage. It's testing of the functionality and more like treated like a black box testing.
Exactly.
And I think that just it's wrong assumption that we end-to-end tests are needed to test the functionality from the user perspective and not trying to understand what kind of methods and code is executed.
You are correct. That is the way that these tests are written. So the intention behind the tests is to test the functionality and not try to maximize some kind of code coverage metric. But still, we can run these tests. And while they are running, we can use coverage profilers to record which methods are getting executed. Because these tools that we use to record this test coverage, they don't really care what is driving the application. Is it a unit test calling a method directly? Or is it someone clicking in the UI in a manual test? Or is it an automated end-to-end test that is clicking something in the UI or calling an API endpoint? In the end, code is getting executed, and these profiler tools instrument the code. So whenever your test is doing something, we can understand which methods are getting executed as a result of this. And this allows us to, let me jump back, to give you these pictures where we know exactly what is covered by a specific test case. And then we can use this to optimize these test cases, even though the way they are written has nothing to do with test coverage and doesn't need to have anything to do with test coverage. So these approaches don't change the way that you write the test. They just help you understand what the test actually does and which of those tests it makes sense to run more frequently. Does that answer your question?
Yeah, kind of. It was understandable. I meant that it's just a wrong assumption that it should not be connected with the code. We are testing the functionality, and we need to optimize the test based on the test cases and importance of the test cases for the user, and not for the kind of related to how many methods we are trying to test. It's like the intention of the end-to-end test it's different. Yeah, but okay.
I understand. I still think these techniques are applicable, even though the way we write these tests and we design these tests and we prioritize these tests is not based on code coverage at the moment. And if this doesn't feel right for your system, the AI test clustering doesn't use the coverage at all. It just uses the content of the tests. So this is basically only the things you put into the test when you design it from a functional perspective. So if this feels better for your system, maybe this is the better approach.
Thank you.
Thank you as well. Any more questions?
None in the chat.
All right. Then I would hand it over to my colleague Johannes for the demo.
Yes, thank you, Fabian. Let me quickly change my screen. So now you should see the demo slide here. Yeah, thank you and welcome also from my side. My name is Johannes. I'm part of Fabian's test intelligence team, where I'm mostly responsible for helping new customers getting started with TeamScale and helping with the configuration, especially in regards to our test analyses. Now, for the first part of our demo today, I want to show you how you can use TeamScale and the Pareto optimization inside of TeamScale. And for that, I brought with me a application. This is called the Digital Bank. And this Digital Bank is a banking application written in Java. Now we use this application to showcase how we can use our analysis in test selection. The digital bank itself can do everything that a banking application is supposed to do. So you can create accounts, you can transfer money, all that kinds of stuff. Now, with that out of the way, I want to jump directly into TeamScale. Right. So this is the login of TeamScale. TeamScale is a server application that can be hosted either in the cloud by us or can be hosted completely on-premise at your servers. Now, I want to quickly log in here with my secret password. And now I'm brought directly to the tests view, the test view inside the metrics perspective. Before I go into detail on what we can see here, I just quickly want to say a few words how you can navigate through TeamScale. So the navigation is done mainly with this bar on the left here. Here we have the navigation sidebar where you can switch between the different perspectives. As I just said, currently we are in the metrics perspective, but there are multiple different perspectives that all connect to analysis of TeamScale. So TeamScale does not only do the test analysis that we showcase today, but others as well, and this is why there are so many different perspectives. Dashboard perspective, for example, shows you some key data points of the projects that are analyzed inside of TeamScale. The activity perspective shows you a nice representation of all the changes happening inside of your repositories or also the test coverage uploads. Findings perspective is mainly relevant for the static code analysis of TeamScale. Then there's requirement tracing. Then we have the test gaps perspective that relates to test gap analysis and also some more administrative perspectives in the bottom. Another way to navigate through TeamScale is via this horizontal bar on top. So the first entry here lets you choose which project you want to have a look at. Currently, we already selected the DigiBank, which is the digital bank, but a TeamScale instance can connect to different projects. So if there are multiple projects inside of your instance, then you can switch between here. And now lastly, there is the branch chooser, which lets you select the branch that you want to have a look at. Currently, we are inside of a feature branch, but we could also select like a release branch, for example, or the default main branch. Now, what you can see here is a table that shows you the test results that were sent to TeamScale. As you can see, the DigiBank currently has 108 tests. Of those, every one was successful, and the duration of all the tests is around 16 minutes. Now we can drill down here a little bit further to see how those tests are currently or where these tests are located. For example, if I go into the acceptance test, then here you can see the list of each individual test case and the duration. And if I now click on one of those, I'm brought to the test detail page. And here I can see, for example, the last test run, the last test result, the duration, and also I can see all the methods that were executed by this one test case. If I hover over this tree map here, I get some additional information on the name of the method and also where it is located. So, for example, the account service Java class here. All right, that is that to the test perspective. Now I want to show you how you can use TeamScale and the Pareto optimization to generate a minimized test suite. For this, we go to the test gaps perspective and then to test selection. Now I am greeted with this perspective here. Before I talk about the risk covering tree map, I just quickly want to tell you how you select the test with which you want to do the Pareto optimization. For example, if we go to select tests here, I can select all the tests which on which I want to run the analysis on. I can filter those, for example, by defining a query or by using a specific name or saying, okay, I want to do the optimization only for tests with a specific runtime or higher than a specific runtime, or maybe only on tests with a certain result. Now, example here, since there are only 108 tests, I will just select all of them, click on selected tests, and now we see that the picture here on the top changed. You can now see on the left all the methods that our test suite came across. And on the right, you can see the coverage over time, which is similar to the picture that Fabian showed before. So you can see those plateaus again. And this is if we run the test in the default ordering. Now, what's left to do is click on this little button over here, which will start the Pareto ranking. And then after short loading time, you see how the tests look like when they are Pareto optimized. So you can already see that in just 14% of the time, we will reach 100% of the relative test coverage. And if you say that you want to maybe spend less time or spend less test budget, then you can use the slider here. And if I, for example, move to the left, you will see how the coverage changes. So now everything that is light blue inside of the tree map are the methods that are no longer covered by the test cases that we selected. Since we now gave even less test budget, there are some tests no longer run, and there are more tests no longer run, and this is why there is some coverage no longer reached. And that's basically already it. All that's left to do is create a list of the tests. So you can see these white tests are the ones that are currently inside of our selections. And what I can do is now also add specific tests where I say those are definitely important because they cover very critical functionality, so outside of the Pareto optimization. And then I can save my list. I can download it as a CSV, for example, or just save it inside of TeamScale for later use. Right, other questions regarding the Pareto optimization? If not, then I would.
There's actually one question in chat. Not sure it's specifically about Pareto optimization, but probably related to using coverage as a proxy for what tests are doing. So in the Pareto approach, you're considering entire methods. So we're looking at which methods are executed by which tests. What about what happens inside the methods? So if there are multiple branches, like different conditions inside the methods, how are those considered by the test selection approach?
Yeah, that's a good question. For the test selection, I would say so the test selection approaches that we present today that use test coverage as a metric, those will operate on method coverage, but you can see inside of TeamScale where the coverage actually runs through. So if the coverage profiler that we use records coverage, for example, on a line level, then you can have a look inside of the source code here and see which lines were reached and which were not.
Sorry, Johannes, I already grabbed the screen share from you. I think you have to grab it back if you want. Actually,
yeah.
My bad.
I didn't
thought you
notice.
were done. Then came the question.
Yeah, that's fine. Sorry. Let me quickly grab it back, maybe. I didn't realize this. So we just maybe if I navigate back. So what I did is I clicked on this method inside of the risk coverage tree map here and clicked on the method history. And now I'm brought to the source code of this method, highlighted in blue here. And everything that is green underlined is a line that is actually executed from the test cases, and everything that is highlighted in red is something that was not executed by the tests.
If I may chime in here to
Sure.
augment this a little bit, I think that was the technical answer. The data would be there. I think from the functional point of view, we did try it out on some systems to use line coverage instead of method coverage for these optimizations. It turns out that it doesn't really add that much more bug finding power in practice. I think the redundancy between these tests, these end-to-end tests, is already quite pronounced on the method level, so that there's not much to be gained, not much more redundancy to be wrung out of there by going down to the line level in practice. So I think for real industry systems, the method level is sort of the good enough approach, because going down to the line level would add more complexity, would add more computing runtimes. It takes longer to compute these lists, and that just doesn't pay off in practice, unfortunately.
Okay. Does that answer the question? I guess so.
I have a similar question, if I may, kind of in the same theme. For example, does it mean, for example, if we have two test cases which covers the same method but different part of the method, they would be kind of considered with the similar coverage, right?
Exactly.
And you choose randomly one of them.
So not entirely randomly, of course. We're considering all the methods that a test case covers. Usually a test case doesn't just cover, if it's an end-to-end test, we just cover one method. So the approach always takes the test case next that produces the most additional coverage per time. This is the metric that really worked the best in our studies. So if you have a test case that covers 100 methods in 10 seconds, and you have another test case that covers 10 methods, 10 additional methods in 10 seconds, and it would take the one with 100, for example.
Yeah, but don't we go in a trap? For example, there are some unit test cases which just kind of calls the method and doesn't do anything in the method. And there are specific unit tests which are testing the method itself. And you will choose the kind of test case which just call them and doing nothing, basically. Right?
I think that's a general limitation of this metric test coverage. We don't really know whether a test case that produces coverage in any method is actually checking something in that method. It's just not in this coverage data.
I understand that because you are not using line coverage right now. And is there a way
line coverage
to expand your kind of representation to add some additional parameters apart from method coverage? I'm wondering. You just told that you did experiments with line coverages, etc.
Yeah, I think line coverage has the same problem. Even if you know that a certain line is covered, you don't know if the test case is actually checking if that line is doing the right thing or not. That's just something that's not in the coverage information. So using the line coverage doesn't give you more certainty about this. But in practice, if we assume that the test suite in general is sane, that it's not just a bunch of test cases that do nothing, right? Then whether we select based on line coverage or based on method coverage doesn't really make a difference if we just want to remove the redundancy there.
Yeah, but you can use, for example, line coverage to do selection. For example, if you have two different unit tests which covers the same method, but you can use line coverage to choose one of those tests to kind of as additional information. I mean, it adds complexity, obviously.
Yeah, I mean, in the end, of course, it will depend on the concrete tests and on the concrete systems. In the ones that we analyzed in our research studies, it didn't make a significant difference. There was some difference, of course, but not enough to warrant the additional complexity. It might be that for your software system, but we would have to check the.
Yeah, sure. Thanks.
Yeah. Thanks for the question.
Maybe one more question from the chat because that just came up. So here again is the aspect of importance of functionality. So basically risk-based testing. And now here we come and say, okay, so we order tests by coverage. How does that relate to riskiness of functionality or importance of functionality?
Yeah, excellent question. I mean, we're not changing the way you design your test suite, right? When you add new test cases, you still do this in the risk-based way. We're just saying that if you want to have a small selection of test cases, these are most likely, statistically, the most likely test cases to find a lot of bugs because they cover stuff all over the system, which is a kind of risk-based approach. It would be kind of risky to only select test cases that cover a small part of the application because then you're not finding bugs in the other parts of the application. So the risk-based approach still applies because you still have, you still run your whole test suite in regular intervals, and all of the risk-based testing approach that you put into your test suite is still there. It's just in these smart selection runs, we use these statistical methods because they just have proven in practice over and over again that they are really good at finding bugs all over the place in the system. Any more questions?
Makes sense. There's some general tooling and integration questions, but I think we'll leave those in the chat for now.
So I will go on to the other approaches that we have and show you what else we can use, what other tricks we can use to get an even better selection where we need to spend less time to still find 90% of the bugs. Now, so far, our approaches have only used information about the test cases themselves. So either the content of the test cases for the AI test clustering or the test coverage of each test case for the Pareto testing. What we haven't used so far, and that we've already touched on with some of the questions, is code changes. So what exactly changed about our system that we want to test? We can use this additional information and get a much better, much more accurate selection for those specific code changes. Now, this changes a bit how these approaches work. Before we were change independent, so we generated one set of tests, and we were able to use this over and over again to check any kind of changes because it covers a lot of the system. Now we're generating a different set of tests depending on what changed. So with every test run of our smart selection, we need to run a different set of tests. We call this change-based testing. Now, how do we even know what changed in a software system? The answer is simply the version control system. So whenever developers check in code changes, we can check in the version control system exactly which lines of code were changed and use that information to make a selection. To show you why this is so powerful, I have a little video here. This is our own code, so team scale. And in orange and yellow, we have all the code changes we made when we implemented a new feature. So our software analyzes other software, so we need to understand a bunch of different programming languages. And in this case, we changed one feature because Java got a new Java version, and we needed to update our parsers and our lexers and so on, so that we can still parse Java in the new version to understand the new keywords and the new language constructs and so on. So all of the colored methods are the methods that were changed to support this new Java version. And what I'm going to do now is I'm going to start a video where every second you see 30 of our end-to-end tests at the time running, and in green the coverage that those produce. First it goes white to see where the current tests are located, and then slowly it fades to green. So you can see how when you run the test suite, it covers different parts of the application. And if you look really closely, you can see that almost none of those tests run through those code changes. And that should not surprise us, because no one at CQSE wrote tests for a Java version that wasn't even released yet. And I think it's the same for many systems. You get a new feature, then obviously no one in advance wrote a bunch of test cases years ago for that feature. So most of the tests that we have cannot find a new bug that was introduced due to these changes, because they're not running through these changes. And in fact, of the 5,000 test cases that we had at the time, only 4 ran through these code changes. All the others will still have the same result as they had before we made these changes. So it really makes no sense to keep rerunning them. So if we know which tests are a good match for our code changes, then we can select those instead of selecting all of the other unrelated changes. And that gives us a much tighter selection and concentrates much more bug finding power in our small test suite. Now, I will not start with the coverage-based approach. I will start with a different approach. So let's say I tell you as a human, we changed something in a new feature. We have this pull request, for example, and we changed something about this web application, about login, accounting, and search. How would you decide which test cases fit well with this change? You would go and you would look at your test suite and you would search for test cases that have something to do with login, accounting, and search. Search is a very well-researched computer science problem. And if Google can index billions of web pages and find out which ones you want when you say new bicycle, then why can't we index your test cases and find the test cases that, that relate to your code changes, that are a good fit for your code changes. And this is basically the idea of the next approach, where we want to find code changes that have a lot of commonality with, find test cases that have a lot of commonality with the code changes. We call this similarity scoring, and the way it works is we index your test cases. So for automated tests, this means the code, and for manual tests, this means the test steps, what the tester has to do, into a database. And then whenever code changes, we can automatically generate a search query for this database from those code changes. So something like search and login and list and user and so on. And then find those tests that match well with those code changes. To show you how this works, I'll use a very simple example from the DigiBank, because I think with this one example, it becomes clear how this works under the hood. Now, what we have here is the transfer function, which is used to transfer money from one account to another account in this DigiBank. And let's assume any line in here changed. Then what we can do is we can look at the whole context of the method, including the comments, and find out what kind of things are being talked about here, what keywords are in here. So something like transfer, accounts, and amounts. This is the same thing that Google does when it's indexing a web page. Now, if I take these 3 example keywords and hold them next to the test cases in the test pyramid of DigiBank, then you can see them reoccurring there. I'll start with a typical unit test. And of course, the unit test needs to create an account. It needs to call this transfer function. It needs to set the amount to transfer. So these keywords reoccur. And then as we move up, for example, to a cucumber test, which describes more the use case, you can see them in here, or a robot test that automates something via the UI, or even a manual test. What do I have to do as a tester? Then these keywords reoccur. So you can see how we can use these keywords to find matches between tests and code changes. Now, of course, not every keyword here is created equal. So something like public and void will not help us find interesting test cases that match this. And on the right side, something like in and the and new are probably also not good keywords to match a test case to a code change. So we really need an approach that differentiates between the keywords that hold a lot of value here to make this match and the ones that do not. And I'll show you in a second how this works in practice. For me as a tester, I don't have to really care about this. I don't even see the search query and the keywords. For me, it feels much more like a Google search. So I'm saying I have this new feature, I have this pull request, please give me the test cases. And then TeamScale gives you a list where the best matching test cases are at the top. Same as with the Google search, the best matching website is at the top. And same as with the Google search, this list is probably long because probably a lot of the test cases in your system have something to do with the code changes. And same as with the Google search, if you land on page 10, you're probably not going to find what you're looking for. So it's the first part of this list, again, that we would want to take and run more frequently. So again, we can define a test budget, say 15 minutes, and take tests from the top until the 15 minutes are full. And this is our smart selection set that we can run much more frequently than the whole test suite. Now, I said it all hinges on us putting the most relevant test cases at the top. So the approach that we use here is one that is well researched in the search engine research community and is used in a lot of search engines today. And it's called term frequency inverse document frequency. What does this mean? It basically has two parts. The term frequency rewards those tests that contain our search terms a lot. So if it contains our search terms 20 times, then it will get a higher score and a higher ranking than if it only contains them twice. And the inverse document frequency punishes those search terms that appear in almost all the test cases. So the more test cases our search term appears in, the less its impact on the score. So something like new and the and don't get a high score, and they don't have a big impact on the ranking in the end. Whereas terms that are really specific to a test case, they are ranked much higher. So if you change something about the code, this test case is very likely to be selected because it's very specifically for that functionality. How well does this work? With this approach, on average, on industry and open source systems, we only need 4% of the time to find 90% of the bugs. Compare that to AI test clustering and Pareto optimization, where it was 11 and 13%. You can see how adding this additional information about code changes, what we actually want to test in this instance, helps us reduce the time that we need to find a lot of the bugs. So this is now something where we can even turn something like a nightly test suite into something that you can easily run for each pull request. So for teams that don't have the ability to run their tests on their pull requests, for example, this can be a great solution to help them make sure that these changes have been tested thoroughly before being merged. Any questions about this approach?
None in the chat so far.
All right. Then let's move on to the last one. Already teased, this one is not using test coverage. Of course, we can, again, if we have this data about which test is covering which code, use this to augment this selection and be even more exact and use even less time to find a lot of the bugs. So if we know for each test case what the coverage is, then we can do what I showed in the video. We can analyze which test case is actually running through these code changes and only select those that actually run through the code that was changed. And with this, which we call test impact analysis, now we only need 2% of the time to find 90% of the bugs. So in some sense, twice as good as the similarity scoring, but it has the drawback that we need to record this test coverage and we need to keep it updated, as we've already seen with the other approaches over time. So depending on how big the pain with your test suite is, it may make sense to spend the extra effort and record this test coverage, or maybe you don't have that much pain, then it's probably okay to use the similarity scoring and spend a little more time testing each time. How is this used in practice? I have one example from Dolby. They make the sound systems that you have, for example, in cinemas or at home in your TV. And one team there is using test impact analysis because they are working on these audio algorithms, and these have a lot of parameters. So you can run a lot of their tests in many different configurations, depending on what kind of speaker and what kind of frame rate and so on. And this means that even with a small amount of tests, they get a huge explosion of test runtime to run it with all of these different parameters. And what they wanted to do is turn their nightly test suite into something that they can run for every pull request and give feedback on a pull request within 10 minutes. So that if a developer checks something in, then we have a good chance of finding new bugs within 10 minutes. And they achieved this with test impact analysis because it has this runtime information about what each test with each particular set of parameters is doing. So we can tell them exactly which parameters they should be running for a given code change. And that helped them reduce their 12-hour test suite to 10 minutes. So this small set they can run for every pull request and find most of the bugs. And they are still doing this, I think 1.5 years later now, even though their test suite grew by over 50% since then. Any more questions about these change-based approaches before we go into a demo?
We have one question in the chat. Maybe it's interesting for everybody. So how do you get test descriptions into TeamScale, especially if you have like manual tests with descriptions? How do you get them into the tooling?
Excellent question. We need to connect to your ALM system where you maintain those. So if you have them, for example, in Jira X-Ray, you would connect to Jira X-Ray, read them from there, or whatever system you use. If you don't have them in such a system, so some of our customers don't use one of those ALM systems, but rather have Excel sheets or text files or Word documents, then we just need to export them in a format that TeamScale can read, something like a CSV file or something like that. Thanks for the question.
Sounds good. No further questions as far as I can see.
Yep. All right, Johannes, then I will hand over to you.
Yes, thank you again. So welcome to part 2 of the demo. For the second part, I want to put on my developer hat and I want to jump into the role of a developer who's tasked with implementing a new feature for, again, the DigiBank. So this is the feature that I'm supposed to implement here. This is the corresponding ticket. I am supposed to add a quick save view, which is a way to quickly store a small amount of money or to save a small amount of money in regular intervals. So for example, 100 euros, and it's supposed to be very easily done. Now, since I'm a very eager developer, I already created the feature. So this is how it looks like inside of the DigiBank. This is the quick save feature. Now, let's jump back to TeamScale to show you how we can how the test impact analysis shows you which tests I need to run now. back inside of the main UI of TeamScale, again on the tests view here, I will now go over to the issues view where I can see all the tickets. And they come from our integration to Jira. So we imported them from Jira in this case. And you can see that there's also a filter already applied. So at the moment, we only see the tickets that are assigned to my user. But I could also say, maybe I want to see all the tickets that are connected to a release. And I can also just define a custom query, very similar to the query language in Jira, for example. And think of a query where I say, maybe I want to select all the tickets that are currently in progress or something like that. That is very highly customizable. I can then save this query and use it later, which is exactly what we did with this my issue query here. All right, now let's jump into the ticket. So here is the add quick save view ticket. As you can see, we have the information coming from Jira, for example, the ticket ID, the title, who created it, who is assigned, and also the ticket description, just like in the screenshot. And then if we scroll a little bit down, we can see the information from TeamScale. So first of all, we see the commits associated to this one ticket, and the connection from the commits and the ticket is done by the prefixing of the issue ID inside of the commit messages, as you can see here. So here we can see the issue ID, and so TeamScale knows which commits are relevant for a specific ticket. And then, most importantly, we can see the test suggestions here. So TeamScale knows about the changes that are happening and knows where the areas are that our test cases run through. So it can suggest exactly which test is relevant to check on the features, check on the feature that I just implemented. As you can see, it is suggesting exactly one test here, which would save us around 89% of our total test execution time. I mentioned it before, but just as a reminder, the total test suite took around 16 minutes. All right, then all that's left for me to do is execute the test that is suggested. I could do this manually, but for the demo, we have automated this. So all that is happening right now is that our build is starting, and then TeamScale is asked which test should we run, and those tests are then exactly executed. Now, what will happen next is our UI test framework will run through the test. And it will execute two tests, even though only one. During the development, I also added a new test. And the new test is important as well because usually I write a test for the changes that I just did. So when querying which tests to run, TeamScale will always also execute the tests that I've newly added. And TeamScale, since I've never run this test before, TeamScale doesn't know about its execution yet. It's just a new test. So as you can see, the Firefox window is now starting here, and we can watch the test runner work. This is the first test, which is currently executed. And then in a short while, after the window closes, it will start again, and the second test will run. All right, so here it's just clicking through the UI. To wait a little bit till we get the results. Okay, now it should close very soon. Great. If I look inside of the console here, then we will see there's a failure, which is usually a bad sign. And more specifically, we can see that there are test failures. Now, if this would be running, if our test would not be running locally like here, but inside of a server, for example, then we might not be able to directly see this feedback inside of the console. But since the test was run, we already got the information inside of TeamScale. So the test results were already sent to TeamScale. And what we can see here is now that the test amount increased. So instead of 108, we have 109 tests now because we executed this new test that I implemented. And we can see that there's one failed test. Now I want to find out which test failed. For this, I click on this little filter button, which will allow me to filter between the tests that we have. I could again do some complicated query, but to make it easier, I will just click on the results here, which will bring me the failed test on top. And if I click on the link here, I will be brought back to the test detail page, which I showed in the first demo as well. But now we have some additional information here. So we can see the test failed in its latest execution. We can see some console output here. And if I scroll a little bit down, I can see the executed methods and the test history. Now, one more thing that we can see here, which we can do because we are using the coverage-based test selection approach, is we can see which methods changed since the last time the test was executed. So we had a previously successful test run, and then TeamScale analyzes all the changes happening inside of the repository. So it knows which methods that the test came across changed in between those two test runs. And this is highlighted inside of this tree map here. And the big orange one is the one that changed in between. And this is a very good candidate to find out why our test failed. So if I navigate into this, I'm brought to the to the method history, which shows me all the commits and test coverage uploads that affect this one method. And if I click on compare method here, I can see a diff view that shows me exactly what changed in between those two test runs. And if I scroll a little bit down, I can quickly identify why my test failed. And that is because during the development of the quick save feature, I commented out some error handling for debugging purposes. And then I forgot to undo this, and this is exactly why my test failed. So now, with this information, I can very quickly construct a fix, which will just remove the comment and enable the error logging again, or the error handling again. And this is what I just did. So now what will happen is the build pipeline will run and the test will also automatically be executed. And which tests TeamScale will tell the test runner. So what you can see here is the activity perspective. As I mentioned earlier, this is showing all the changes that are happening inside of the repository. And this is the commit that I just did to fix the bug that I introduced earlier. And if I click on this commit, you will also see the test suggestions. And now TeamScale will execute exactly that one test because it is the one, exactly that one test. So as you can see, the test suggestions not only work on a ticket level, but also on each individual commit, or for example, for a merge request or pull request. Now we can watch the test runner again. So the test will be executed again. And this is exactly the test that was also initially suggested in the ticket. All right, so now the execution is done. And if I look inside of the console again and wait a moment, then we can already see the success, but we can definitely also see it inside of the test perspective from earlier, where we can now see we have 109 tests and all of them were successful. Now, just to summarize here, I want to quickly jump back to the slides because what happened, what we just were able to show you is when the regular continuous integration pipeline, for example, would take 16 minutes to run all the tests, we were able to run the important tests, identify that something broke, do the bug fix, run the test again to see that the bug fix actually fixed the bug, and doing all that in less time than it would take to actually run the whole CI pipeline. And that is even though the test only takes 16 minutes. So here we can see the immense benefit that the test impact analysis brings. All right, that would be it for the second part of the demo. Are there any questions?
No questions in the chat at this point.
I do have a question. What about the suggestions? I think in the slides you showed that this is also possible for manual tests. What about if the manual tests are written in another language like German?
Should I take over that question, Johannes?
Yeah, gladly.
I will just grab the screen share real quick. Right, yeah, thank you very much for that question. I think it really depends on which approach you use. The test coverage-based approaches don't really care what language your tests are written in because they only take the test coverage into account. For the similarity search, of course, if your tests are in German and your code is in English, then we would need to do an automatic translation in between to be able to still do this keyword matching.
But this automatic translation is also part of TeamScale, or?
Not at the moment. So we don't have a customer yet that has this particular setup. If this is interesting for you guys, we can check how much effort this would be to implement something like that.
Okay, thanks.
Yeah, you're welcome. Further questions? Otherwise, looking at the time, I would wrap it up. So we've shown you two different ways you can make such a smart selection of a small amount of tests. The change independent way with Pareto optimization and AI test clustering, where we try to select tests that are not redundant, that are not testing the same areas of the application over and over again, but rather tests that go over the whole application so we have a chance to find bugs everywhere, even if we make a small selection. And the change-based approach, where we understand which changes we want to test and then select tests that specifically match those changes, either because the tests talk about similar things than the changes, or because they run through the changes based on code coverage. And that gives us 4 approaches with different trade-offs in terms of what kind of precision you get from the approach and how much effort you have to spend to make the approach work. And so depending on how much pain you have with your test suite and your testing process and your software system specifics, it may make sense to take the one or the other. For most of our customers, it will probably make sense to start in the lower left, try out the least effort approach, and then move to a more advanced approach if this doesn't give the results that you're expecting. But either way, you can also combine these approaches. So for example, you could run AI test clustering on your main branch to regularly give feedback on bugs all over the place, because this selects tests that cover almost the entire software system. And on feature branches where you have pull requests and you want to give really fast feedback to developers about their specific changes, use something like similarity scoring or test impact analysis to give the fastest feedback possible. And make sure these changes are tested before merging. No matter how you combine the approaches, no matter what you use in the end, they help you shift most of the bugs to the left because you can run these small selections much more frequently. And since they have a lot of bug finding power, more than the whole test suite on average, you can find most bugs earlier. So I hope I was able to show you how this can be useful. If you have any more questions, now would be the time before we wrap it up.
Just a short question, if I may.
Yeah.
Did you do any comparison of which tests are chosen by these two different approaches? I mean Pareto and AI-based. How different the tests which are chosen by those two methods for techniques?
Yes, sort of. I'm not sure it's 100% what you want, but I'll tell you what we did, and then you can tell me if this is what you meant. What we did is we ran the AI test clustering and the Pareto testing on the same system. And on the one hand, we checked how many bugs do we find, but on the other hand, we also checked what kind of test coverage does the AI test clustering generate, and is this similar to the Pareto result or not? And we find that it's the same as you saw in the bug finding numbers. The amount of test coverage that you get is close to what you get with Pareto testing, but it's not exactly the same. It's a little bit worse because we have a little less information. So from that, I would deduce that it's selecting sort of similar things, but not exactly the same things. Does that make sense?
But in terms of specific tests which are chosen for this small subset of tests, are they very different or are they more or less similar? I mean, the test names.
So we did with the customers that we already ran the AI test clustering, we always ask them this question. Do you think these tests are different from each other? They are varied, they are covering a lot of the different functionality. And so far the answer was always yes.
I see.
Sounds good. In the interest of time, I'm going to chime in here. We still have a couple more questions, and we're happy to continue answering them. But since we're at the end of our allotted time slot, I would like to close this session to give everybody else the freedom to leave to their probably lunch for most. I learned never to stand between people and their food. So that's the time again to thank you, Fabian, and Johannes, for giving this presentation. Everybody who attended, for all the interesting questions, that we're already at the end of a time slot. It is a good sign because it means we had many discussions. So thanks again here for participating. Thanks for chiming in and asking your questions. Maybe to close here, if you want to dive deeper into this topic and maybe also discuss how does this work at my place, then we are also happy to host similar workshops at your end. So just ping us, and we're happy to give similar presentations in your context, also specific then to your setup and your technologies in use and your testing stages. To make this like more customized. And if you're interested in our testing topics in general, then we have another workshop coming up at some time until then, but maybe you can bear with us until December to look into how we can actually find untested changes in our code, so ones that we don't currently have any tests for. This will be Johannes and Stefan presenting then. So if you're interested, already sign up. And with that, I'm at the end here of the official part. It says thank you again. We'll open our feedback poll at this point. It's already popping up. So if you give us some feedback, we'd be very happy. And otherwise, I'll leave you to your lunches. And if you have more questions at this point, feel free to stay. We'll be here some more time to answer your questions if you have them. Thanks, everybody.
Thanks for me as well.
Thank you.
So there was one more question in the chat. I only have to find the chat since I took over screen sharing. The whole layout changed. So what happens to, I guess, all these approaches if test names change? So TeamScale knows about tests and somehow the basis for deciding what you can execute. What happens if test names change over time?
Also a good question. Depends on the approach again. So for the approaches that only take the test content into account, usually we connect directly to the systems where the tests are stored, so either version control system for code tests or the ALM system for the manual tests. And then we can automatically see that the test was renamed, and we can take this into account and suggest a new name instead of the old name. For the test coverage-based approaches, you need to tell TeamScale about this renaming so that it can associate the old test coverage with the new test. We can't know automatically that the test name changed and it still has the exact same coverage and it's the same test than the other one.
Okay, seeing there's no more questions popping up at this point, neither in the chat nor on the audio, I would suggest we close this session down.
All right. Thanks to everybody who stuck around until the end.